In this geometry video, we have a third type of transformation, the translation. First was reflection, where we reflected across a line or an axis. Second was rotation, where we took the pre-image and we rotated it around a point of rotation. And for this one, translation, what we're doing is we're taking this, whatever we're starting with here, we call our pre-image, and we have a, what do we got here? Hexagon. This hexagon is going to be moved. Basically that's it. It's just taking it from one place, moving it to another. We don't rotate it, we don't reflect it, we translate it. And in order to do this, we need a vector. Okay, the vector tells us in which direction and how far. So what I've done here is, if there is no vector at all, then there is no translation. But as I increase the length of the vector, that determines the length of the translation, as does the angle. So when we talk about our translation vector, if we're looking at it in a polar way, what we want to do is kind of think of this as a rotational direction. That means maybe we go some number of degrees from 0. So this is where we would start at 0 degrees, and then this would determine our rotational direction. The word magnitude is asking how long is the vector, or what is this length, or how far from C to C prime will we go. And so what I can do here to kind of illustrate that is, if I move this vector, you'll see that it is exactly the distance from D to D prime, from E to E prime, or from any point on this polygon to the corresponding point on its translation. Now, instead of talking about rotation and magnitude, there's another way we can talk about vectors and translation, and that would be using what we would call a rectangular model. Okay, so this rectangular vector is being controlled by two sliders here. So this slider is adjusting what we would call the horizontal component. So maybe it'll be helpful if I use like a little right triangle and pretend that these are nice and straight, but I think you'll get the idea here. So if we use this as a right triangle, this value, the x component, is like one leg of a right triangle, and this value, the y component, is like this leg of a right triangle. And then the hypotenuse is what we would then call our vector. So instead of talking about degrees and length, all we're going to do to describe this vector is we're just going to describe horizontal and vertical. And so as I drag my slider, you see that now my horizontal component is 12, while the vertical component is still at 6. I could adjust this, and now I've just changed my vertical component to 4, while the horizontal remained at 12. Okay, so these are the controls I have for this vector, and let's just put it at, how about 5, 4. Now a commonly used notation for this would be with these little angle brackets. Forget that little thing right there. But 5, 4, and these little angle brackets, this is what we would call vector notation, and more specifically component form. Alright, now let's get back to the transformation here. The way I constructed this is, as I change the horizontal component of this rectangular vector, the exact same components, or the exact same vector, is being used to translate B to B prime, or to translate A to A prime, or to translate C to C prime, which we can't see anymore, so let's drag this back. And that would be true for any point on the pre-image, will translate to the corresponding point on the image according to the components we have. Now, this can be not so difficult of a problem if you understand components. You can also easily find the coordinates of any point on the image. Like, let's say, for instance, if all I knew were the components 4 and 10, and I wanted to find the coordinates of A prime, remember, x is always our horizontal, so what happens when I add 10 to 4? For the x value, we get 14. What happens when I add 4 to negative 4? I get 0. Right? And we see the same pattern. Adding 10 to the x value of b gives me the x value of b prime. Adding 10 to the x value of c gives me the x value of c prime. And the same is true for the y component. If I add 4 to negative 7, I get negative 3. If I add 4 to negative 8, I get negative 4. And this leads us to another way that this notation can be written. Is this vector could also be written in parentheses as x, and this is a positive component, so that would be plus 10, and then y, this is a positive 4 component, so this would be plus 4. And you'll probably see that in your textbook sometimes when they're explaining what the components are for a rectangular vector which leads to a translation.